So as we saw earlier, we had a couple of vectors in a plane, and it didn't really matter. There was one vector that that went 3 over and 2 up, and it was the same as the vector that started at 2, 2 and went to 5, 4. They were the same vectors. So it doesn't really matter, it seems, where the initial position of the vector is, the initial point. We can always kind of take the point and slide it so that it's at the origin. So let's write that down. A vector can always be moved so that its initial point is at the origin. We can say 0, 0. All right, and so when we move the vector to the origin like this, we slide u so that the initial point is at the origin, then the vector is determined by its endpoint. Is then determined by its endpoint. A, comma, B. And so that is to say, in this picture, that u, the vector u, is equal to the endpoint 3, 2. And it's written just like a point is written. The only thing that kind of clues you into that it being a vector and not a point, this is a big fat comma, is this little the arrow on top of u. Okay, so it's determined by just a pair of points like this. And earlier, if you look back at the other example, v was determined, it was basically the vector 2, 3, and if you were to figure out w, it had the same slope as v, but it was shifted up 1, so if you kind of slide it down to the origin, it would have x-coordinate 1 and y-coordinate 3 halves. So you can look back at u, v, and w from earlier and try to figure these guys out. 3 over 3 comma 2 for u, v is equal to 2 comma 3, and w is 1 3 halves, or 1.5. Okay. So those are some examples of writing them as numbers, or as pairs of numbers. Now you might ask the question, how do you figure out the length of this arrow? How do you talk about the magnitude when you know these points, when you know the endpoint of the vector, like this? Well, the length is simply the Pythagorean length. It's the length of this right triangle, the hypotenuse. So let's determine that. For the case of u here, you would take the square root of 2 squared and 3 squared. So calculation of magnitude and direction. So if v is a vector equal to a comma b, so some real numbers a and b, then the magnitude of v, denoted, a lot of words, denoted v with absolute value bars on either side of it, is equal to square root of a squared plus b squared. I'll summarize this in a moment. So that's telling you how to find the magnitude. The magnitude is the square root of the sum of the squares of the coordinate. It comes from the Pythagorean theorem. And then the direction of v is determined by an angle. By the angle theta, where this is theta right here. Theta is the angle the vector makes with the positive x-axis. It's determined by the angle theta, which is equal to tan inverse of b over a. We can box this one. We can box this one. Magnitude equals that. But you have to be careful with this one because this doesn't care if, so if b and a are both negative, b divided by a is positive. However, you know where b and a being negative would be is down here, is in quadrant 3. So you have to be mindful of this, where theta is chosen so that cos theta is the same sign as a, and sine theta is the same sign as b. Basically, sometimes you're going to have to add pi. You're going to have to add pi to this if it ends up being in quadrants 2 or 3. It's basically the case. So let's do an example of calculating the magnitude and direction or an angle of a vector with this example u right here. So since u equals 3, 2, the magnitude of this vector, you see that all right? Yeah. U equals 3, 2. The magnitude equals the square root of 3 squared plus 2 squared, which equals the square root of 9 plus 4 equals the square root of 13. So that's the magnitude of this vector u. And then the magnitude, or the direction or angle of this vector theta equals the inverse tangent of 2/3. 2 divided by 3, this number divided by this one. And this is approximately equal to, I need to calculate this one real quick. 2 divided by 3, inverse tangent, is approximately equal to 0.588. Is that right? 2/3 inverse tangent, 0.588. Sweet. Yeah. Okay.